Good morning to all. Today I would like to discuss with you about momentum representation using Fourier analysis. In this video, I would like to solve two problems in momentum representation using Fourier analysis. Before going to momentum representation, we must know the difference between position space and momentum space. In quantum mechanics, a particle is described by a quantum state. This quantum state can be represented as a superposition of basis states. It is our freedom to select the set of basis states as long as they span the space. If one chooses the eigenfunction of position operator as a set of basis functions, one speaks of a state as a wave function in position space. If one picks the eigenfunctions of the momentum operator as a set of basis functions, the resulting wave function is said to be the wave function in momentum space. So, position space, it is also called real space or coordinate space, is the set of all position vectors, let's say R in space, and have dimension of length. Momentum space is the set of all momentum vectors, let's say P, a physical system can have. We all live in a dynamic universe and absolutely everything is moving. There is essentially no such thing as a stationary object. In normal space, we define something by where it is, of course, relative to something else, and when it was there. That means we are dealing in space-time coordinates because it will have moved on later. In momentum space, we describe something by how fast it and in what direction it is moving with respect to something else. It is to a certain extent the other side of the dynamics of the universe. This can be very useful in high energy physics experiments like the Large Hadron Colliders, which happened in very tiny volume and over incredibly short time periods. So you can only measure what went in what direction and with what energy. So in some problems in physics, we are dealing in momentum space rather than in position space. Now let us have a review about all these terms. I'm dealing in position space. Let psi of x is the wave function in position space. Then psi star x psi x dx. It is called position probability density, the probability of the particle being at a given location, let's say between x and x plus dx. Now integral minus infinity to plus infinity psi star x psi x dx equal to 1. That is the total probability, the probability of the particle being in the entire space is equal to 1. Next deals with the position expectation value. Actually, expectation value, it is the mathematical average of large number of measurements done on similar system at an instant, or mathematical average of the large number of measurements done on a single system at various time. Similarly, coming to momentum space, let's say Gp is the wave function in momentum space. So this is complementary to the position space wave function psi of x. So first, G star p Gp dp, rather than telling us the probability of the particle being at a given location, Gp is the probability of it having a given momentum. So integral minus infinity to plus infinity G star p Gp dp equal to 1 is the probability of particle having a momentum in the entire space is equal to 1. Then this is the expectation value of P in momentum space, integral minus infinity to plus infinity, G star P, P, GP, dP. So I just conclude what I discussed so far. Position space is a set of all position vectors are in space and have the dimension of length. Momentum space is the set of all momentum vectors P a physical system can have. And the momentum space wave function Gp is complementary to the position space wave function psi of x. Gp, the probability of it having a given momentum. The commutation relation of P and x is minus I squared. When we consider a special wave function psi of x, then the commutation relation of P and x on psi of x is equal to minus I squared psi of x. This is in position space. In position space, x stands as x and P should be written in terms of x as minus I squared dou by dou x. When we consider same commutation relation in momentum space with wave function g of p, that is g of p is the wave function associated with momentum space, then the commutation relation of p and x on gp is minus I squared gp. Here in momentum space, p stands as p and x should be written in terms of p as I squared dou by dou p. Now, if a function is given in position space, its Fourier transform gives you its value in momentum space, and the inverse transform of momentum space function gives you its value in position space. Let us consider a function f of t which is in time domain and f omega a function in frequency domain. Then the general equation for the Fourier transform is f omega is equal to 1 by root 2 pi integral minus infinity to plus infinity f of t e raised to minus I omega t dt. Similarly, let psi of x be a wave function in position space and gk is the corresponding wave function in momentum space. Then Fourier transform of psi of x gives you the momentum space function gk. Therefore, gk is equal to 1 by root 2 pi integral minus infinity to plus infinity psi of x e raised to minus ikx dx. And the inverse transform gives you psi of x, that is psi of x is equal to 1 by root 2 pi integral minus infinity to plus infinity gk e raised to ikx dk. Now for our analysis, we have to convert gk in k space in terms of p. We know p is equal to h squared k. But remember, the wave function gp is not simply gp by h squared. There is an additional term 1 by root h squared. Why? Because we have integral minus infinity to plus infinity g star k gk dk is equal to 1. Therefore, we have to consider 1 by root h squared also with gk while writing in terms of gp. Therefore, gp is equal to 1 by root 2 pi h squared is there, integral minus infinity to plus infinity psi of x e raised to minus I px by h squared, because k is equal to p by h squared dx. Then the complex conjugate is g star p is equal to 1 by root 2 pi h squared integral minus infinity to plus infinity psi star x e raised to I px by h squared dx. In three-dimensional case, Gp is equal to 1 by 2 pi h cut raised to 3 by 2 triple integral psi of r e raised to minus I r dot p by h cut dq bar. We have to remember all these three equations for our further analysis. Our first problem is to find the momentum wave function associated with the ground state of hydrogen atom. We are doing this using Fourier analysis. The special three-dimensional wave function associated with the ground state of hydrogen atom is given by psi of I is equal to 1 by pi a0 cube raised to 1 by 2 e raised to minus r by a0, where a0 is the bar radius, which is equal to 4 pi epsilon 0 s square by m e square. Now, to find the momentum wave function, we have to use transformation equation. So, our transformation equation to the momentum space is Gp is equal to 1 by 2 pi h cut raised to 3 by 2 to put integral psi of r e raised to minus I p dot r by h cut dq bar. This is the special wave function for hydrogen atom. This is the transformation equation for momentum space. Therefore, when we are substituting psi of r here, we obtain g of p is equal to 1 by 2 pi h cut raised to 3 by 2 into 1 by pi raised to half a0 raised to 3 by 2 integral e raised to minus r by a0 minus I p dot r by h cut dq bar. Now we have to find the value of this integral. For this, we can use this general equation, e raised to minus ar plus I b dot r dq bar is equal to 8 pi a by s square plus b square the whole square. When we compare these two equations, we have a is equal to 1 by a0, here 1 by a0, here b is equal to minus p by h cut. So when comparing these two equations, we obtain a is equal to 1 by a0 and b is equal to minus p by h cut. Therefore, our solution Gp is equal to 1 by 2 by h cut raised to 3 by 2 into 1 by pi raised to half a0 raised to 3 by 2 into, here we have 8 pi a by s square plus b square the whole square. Therefore, 8 pi instead of a we have 1 by a0 here, 1 by a0 square plus b square, that is p square by h square the whole square. Now, rearranging all these, we obtain Gp is equal to 2 raised to 3 by 2 by pi a0 raised to 3 by 2 s cut raised to 5 by 2 by a0 square p square plus h square the whole square. This is obtaining by rearranging all this. For example, when we consider a0, here we have a0 raised to 3 by 2 and a0. That means a0 raised to 5 by 2. In numerator, a0 raised to 4, and we have in denominator a0 raised to 5 by 2. So therefore, a0 raised to 4 minus 5 by 2. That is 8 minus 5 by 2. That is 3 by 2 here. a0 raised to 3 by 2. Here we have s cut raised to 3 by 2, and in the numerator we have s cut raised to 4. So when this goes to numerator, it's minus 3 by 2. Therefore, 4 minus 3 by 2, that is 8 minus 3 by 2, s cut raised to 5 by 2. Like that, we obtain the general equation as the momentum wave function for hydrogen atom in the ground state is Gp is equal to 2 raised to 3 by 2 by pi a0 raised to 3 by 2 s cut raised to 5 by 2 by a0 square p square plus h cut square the whole square. This is the simplest way to find the momentum representation of hydrogen atom using Fourier analysis. There are so many other methods to find the momentum representation. I will show you a paper regarding this. This is a very old paper, 1972, published in 1972 by wash. This is a little bit complicated. So this is the overview of our problem. First of all, we have to write the spatial three-dimensional wave function of the ground state of hydrogen atom. Then the transformation equation for the momentum wave function. Then we are substituting this general integral. Finally, we obtain Gp is equal to 2 raised to 3 by 2 by pi into a0 raised to 3 by 2 s cut raised to 5 by 2 divided by a0 square p square plus h cut square the r square. This is the solution for our first problem. So our second problem is to find the momentum wave function of harmonic oscillator using Fourier analysis. The classical Hamiltonian is kinetic energy plus potential energy is equal to total energy, that is p square by 2m plus half kx square is equal to E, where k is Hooke's constant. Now in classical mechanics we have p square by 2m plus half kx square is equal to E. Coming to quantum mechanics, we have Schrodinger equation, or Hψ is equal to Eψ. So we have to move to operator analysis. Instead of p square, we have p square operator. Instead of x square, we have x square operator. Remember, we are dealing it in position space. Therefore, for x, we are keeping x, and for p, operator p, we have to replace it like minus I h cut dou by dou x, or in terms of x. Therefore, when we are writing the Schrodinger equation, instead of p square, we have to take the square of this minus I h cut dou by dou xi. Therefore, minus h cut square by 2m dou square psi of x by dou x square plus half k operator x square psi of x is equal to E psi of x. This is the Schrodinger equation in position space. So, normalized wave function is psi of x is equal to e raised to minus root mk by 2 h cut into x square, and the energy in the ground state is equal to root k by m into h cut by 2. So far we are dealing in position space, therefore Schrodinger equation is minus h cut square by 2m dou square psi of x by dou x square plus half k x square psi of x is equal to E psi of x. If we are dealing it in momentum space, remember P stands as P as such. X should be replaced in terms of P, therefore I h cut dou by dou P. So coming to Si is equal to Esi. Here operator P square, we have to keep it as P square, then by 2m. G of P is the wave function momentum space. Then instead of operator x square, we have to use the square of this I h cut dou by dou p the whole square, therefore minus h cut square k by 2 dou square gp by dou p square is equal to egp. So the solution for this can be obtained in so many ways. This is a paper regarding this harmonic oscillator, eigenfunctions in momentum space. This is a very lengthy derivation. But we can simply derive it from our Fourier analysis. Now in Fourier analysis, we are using a spatial wave function psi of x is equal to e raised to minus root mk by 2 h cut into x square, and the transformation equation for momentum wave function g of p is equal to 1 by root 2 pi h cut integral minus infinity to plus infinity psi of x e raised to minus ip x by h cut dx, same as that we did in the case of hydrogen atom. So now we have to substitute for this psi of x here and find the integral and rearrange it and obtain the solution. Now psi of x is equal to e raised to minus root mk by 2h cut into x square. We are substituting it here. Therefore, Gp is equal to 1 by root 2 pi h cut integral minus infinity to plus infinity e raised to minus root mk by 2h cut into x square, that is our wave function, into e raised to minus ip x by h cut dx, that is here. Now when we rearrange it, this is like 1 by root 2 pi h cut integral minus infinity to plus infinity e raised to minus root mk by 2h cut s square minus ipx by h cut into dx. We have to solve this integral. For that, we can consider the Gaussian integral minus infinity to plus infinity e raised to minus x square plus bx dx, which is equal to e raised to b square by 4a into root pi by a. Here, when we compare these two integrals, we have a is equal to root mk by 2 h cut and b is equal to minus ip by h cut. Substituting this, we have Gp is equal to 1 by root 2 pi h cut into root pi by root of mk raised to half divided by 2 h cut. That is from this root pi divided by a. We have a is equal to root of mk by 2 h cut. So root of root mk is equal to mk raised to half divided by 2 h cut into e raised to b square by 4a. E raised to b is minus ip by h cut, therefore b square is equal to minus b square by h cut square into 1 by 4 into 1 by a. A is root of mk by 2h cut, that is 2h cut by root of mk. So when we rearrange all these, that all you can do by yourself. Finally, we obtain the momentum wave function GPS 1 by mk raised to 1 by 4 into e raised to minus b square by 2h cut into root mk. This is the unnormalized solution. Gb is equal to e raised to minus b square by 2h cut root mk, and the energy value is same as that of position space. E is equal to root of k by m into h cut by 2. Before concluding, what we did was, first we wrote the spatial wave function for each problem, then the transformation equation for the momentum wave function, then we found the solution. Thank you.